welcome to Mechanical Gyan Hub. In last video of heat transfer, we had seen first point, the difference between thermodynamics and heat transfer. Second point, mode of heat transfer. Third point, what is conduction and its examples. Fourth point, if diamond is non-metal, then why it has a very high thermal conductivity. Fifth point, electrically good conductors are also good conductors of heat. And sixth, last point, what is thermal conductivity? Friends, in this video we will see examples of thermal conductivity and thermal conductivity versus temperature and governing laws of heat transfer. Friends, before thermal conductivity examples, we will recall definition of thermal conductivity. Thermal conductivity is denoted by K. It is the ability of material to allow the heat energy to get conducted through the material quickly. It is a thermophysical property of a material. Materials which have very low thermal conductivity known as insulators. It prevents the conduction heat transfer rate. Friends, generally we think conduction occurs in solid only, not in gases. Based on this, we will see one question: does conduction occurs in gases? Its answer is yes, conduction occurs in gases. Consider two plates, one plate at high temperature and other plate is at low temperature. Molecules have high temperature near to high temperature plate and molecules have low temperature which is near to low temperature plate. Gap between low temperature molecules is very narrow, so it can be considered as in rest. And the high temperature gas molecules have high velocity and the low temperature molecules have low velocity because according to VRMS velocity from kinetic theory of gases, VRMS is equals to square root of 3 mRT, where T is the temperature in degree Kelvin. So velocity of gas is directly proportional to a square root of temperature. Hence, at high temperature velocity is high and at low temperature velocity is low. So heat conduction occurs in gases by molecular momentum transfer when high velocity high temperature molecules collide with the low velocity low temperature molecules. Friends, in general, gases are very bad conductor of heat and its thermal conductivity is equals to 0.026 watt per meter Kelvin. Friends, we will see question: does thermal conductivity depend on temperature? If yes, then why? Friends, as the temperature of the gases increased, their thermal conductivity also increased because at high temperature of gas, greater molecular activity may result in more number of collisions per unit time and hence more momentum transfer rate. Friends, here thermal conductivity versus temperature graph as shown in figure of H2, helium and air. As temperature increases, thermal conductivity also increases, or we can say thermal conductivity is directly proportional to temperature. Friends, liquids are better conductors of heat than gases. Among all the liquids, mercury has the highest thermal conductivity. Due to good conduction, good expansion, good low vapor pressure of mercury, mercury is thermometric fluid. Friends, now we will see governing law of heat transfer. First, Fourier's law of conduction. The law states that the rate of heat transfer by conduction along a given direction is directly proportional to the temperature gradient along that direction and is also directly proportional to the area of heat transfer lying perpendicular to the direction of heat transfer. Here capital Q, consider capital Q is the heat transfer and small q is the heat transfer rate. Here Qx means Q is the heat transfer rate and X is the direction perpendicular to the cross section area. According to this law, Qx is directly proportional to minus dt upon dx, where negative sign shows that heat always flows in the direction of a decreasing temperature, that is to satisfy Clausius statement of second law of thermodynamics. And dt upon dx is the temperature gradient. And Qx is directly proportional to area. So combining equation 1 and equation 2, Qx equals to minus Ka dt upon dx, where K is the thermoconductivity, which is thermophysical property of material. Friends, second law here, Newton's law of cooling. It is for convection of heat transfer. Friends, we will see convection in detail after completion of conduction. When cold fluid passes on hot plate, then convection occurs. The law states that the rate of heat transfer by convection between a solid body and a surrounding fluid is directly proportional to the temperature difference between them, and is also directly proportional to the area of contact or area of exposure between them. That is, Q convection is directly proportional to the Tw minus T infinity, where Tw is the hot plate temperature and T infinity is the fluid temperature. Q convection is directly proportional to the area. Combining equation 1 and equation 2, Q convection equals to HA Tw minus T infinity. Its unit is watt. H is the convection heat transfer coefficient and its unit is watt per meter square Kelvin or watt per meter square degree centigrade. Friends, K is the thermal conductivity and it is a material property, but H is not a property of material, but it depends upon some of the thermophysical properties of the fluid, like density, specific heat, thermoconductivity, and viscosity. In friends, convection are of two types: forced convection and free convection. We will see in detail. In forced convection, convection heat transfer coefficient is the function of velocity, dimension, density, specific heat, thermoconductivity, and viscosity. While in free convection, convection heat transfer coefficient is the function of gravity, isobaric volume expansion coefficient, change in temperature, dimension, specific heat, density, viscosity, and thermal conductivity. Friends, range of H in different conditions. For free convection in gases, H equals to 3 to 25 watt per meter square Kelvin. For forced convection in gases, H equals to 25 to 400 watt per meter square Kelvin. Free convection in liquid, H equals to 250 to 600 watt per meter square Kelvin. Forced convection in liquid, H equals to 600 to 4000 watt per meter square Kelvin. Condensation heat transfer, condensation means vapor to liquid conversion. Then condensation heat transfer, H equals to 3000 to 25000 watt per meter square Kelvin. Boiling means liquid to vapor formation. Boiling heat transfer H equals to 5000 to 50,000 watt per meter square Kelvin. Friends, third law, Stefan Boltzmann law of radiation. This law states that the radiation energy emitted from the surface of a black body per unit time per unit area is directly proportional to the fourth power of the absolute temperature of the black body. That is, EB is directly proportional to T raised to power 4, where T in Kelvin only, and EB is the emitted energy of a black body. Therefore, EB equals to sigma into T raised to power 4. Its unit is joule per second meter square या watt per meter square, where sigma is the Stefan Boltzmann constant and its value equals to 5.67 into 10 raised to minus 8 watt per meter square Kelvin raised to 4. Friends, black body is the body which absorbs all the thermal radiation incident or falling upon the body. Friends, black body is the perfect absorber, ideal emitter and diffusive in nature. Friends, black body absorbing all the incident thermal radiation falling upon it, it may not appear black in color to the human eye. And its example is ice and snow. Friends, we will stop this lecture here. In next lecture, we will see derivation of Fourier's law. Thank you.